you're going live on YouTube.
Okay.
And, oh, we're going to switch it to this one. Oh, can you click go live on the...
I don't...
Yep, you got it. You're there.
Oh, you switched them. Woo woo!
You want to keep it like that, popped up. Because that makes it much bigger. Yeah.
I see. There you go.
Cool.
All right, go get those rotten kids. Yay, Lucas Math Up Show! Woo woo! Math Thursday, it's time. Guess what today is? Math Thursday. Boop boop. All right. All right, guys, welcome to Math Thursday. If you have any questions, any concepts that you need, I know it's getting ready to be time for a lot of finals and things like that, or, you know, just tests and stuff like that, you know, put it in the chat and we will get into it. So look at this. I got all new boards. Ooh, they're reversible now. And so now it's a nice grid and it doesn't feel quite so tough on the eyeballs. And I also got a ton of markers. There's some really cool expo colors that are out right now, but yeah. With eigenvectors, hi Malik. Eigenvectors, I don't know. That may be beyond me. What class is that for? Let's see. What have we got? Eigenvectors. Eigenvectors? Oof. All right, we got some vectors. Thank you. Always happy to hear from a fellow teacher. Oh, eigenvectors, getting into linear algebra. Oh, man. That's a little bit beyond what we are doing here. Primarily, we're looking at like algebra 2, trig, into some pre-calc. But linear algebra in the Lucas, I can definitely do piecewise functions for you. Lucas, remind me of what math level that you're in. One stem. Okay. All right. So Lucas is asking about piecewise functions. Piecewise functions. There we go. Algebra 1 makes more sense. All right. So Lucas is asking about piecewise functions. So piecewise functions are, well, I mean, like a function is something like, you know, whenever you're primarily whenever you're graphing things and when you're first learning how to graph things, you're really focusing on functions. Okay, so functions can be linear, like a straight line. They can be a parabola, right? They can do anything as long as there's something called the vertical line test. So the vertical line test, let me grab a pencil, is if you have, I might be able to see. I'll use that. So with the vertical line test, if you have a line that, like this one, we could have one like this, right? And then we could have one like, let's do one in blue, something like this. Okay. So the vertical line test is one way that you can figure out if it's a function or not. So basically what a function is where you have an input that gives you an output that you know what it's going to be, right? So if I plug in 1, I'm going to get 5 every time. I'm not going to plug in 1 and maybe get 5, maybe get 6, okay? So one way to check that is with something called the vertical line test. So if you pass a vertical line over your graph, then you can determine whether it's a function or not. So passing the vertical line test means that it's only going to cross through the line or the function in one place. Okay? So this curvy line here and this straight line here, two different functions, but they are both functions, because if you look, and actually, you know what? I'm going to change the color of this one. Let's do this one in purple so then we can really see. Right. Okay, so the pink line here, even though it's curved, it's still, if I look at this vertical line, right, it's only going to pass through one spot. Whatever I plug in for my x value, I know what I'm going to get for my y value, right? So here, if I plug in 2, if I plug in 2 for my x value, I know I'm going to get -3 for my y value, just always, right? If I plug in, let's see, if I plug in 0, I'm going to get like -3.5 for my y value, right? So I can also look here with this purple line, right? So we're looking at this purple line now. Same idea, right? There's only one output for my input. So if I plug in 1 for this one, I'm going to get +4. Okay. Now this one here, this this blue-green curve here, this is not a function, because if I look at it, right, it passes through that vertical line twice, okay? So what that really means is that I don't know what I'm going to get out when I plug in my x, right? So I can plug in 1, 2, 3, 4, 5, 6, 7. So if I plug in -7 for my x, I'm either going to get 4 or 9. I don't know which one I'm going to get, okay? So this is not a function, okay? So this does not meet that definition of the function, okay? So you do know what the values are going to be, but the problem is that when you put in your input, it's not an output. So you can still write an equation for this, right? Like there's equations for circles, but even circles are not functions because they don't pass that vertical line test, okay? That doesn't mean they aren't a thing, right? They just mean that they're not a function. That's okay, right? It doesn't have to be a function. You can still graph it. But most of the time, especially when you're in Algebra 1, Algebra 2, the vast majority of equations you're going to be dealing with are functions, okay? So with these functions, oh my gosh, look at these cute little erasers that came with all of my dry erase boards. Are so cute. Okay, so a piecewise function, okay? So a piecewise function, I know I've said this a million times. Ooh, it's IE, right? Piecewise function, okay? So I know I've said this a million times on this site and in these videos and everything, but mathematicians are not terribly creative with naming things. So piecewise function just means that it's literally a function that's split into pieces. That's it. A function that's split up into pieces. Okay? So when we look at this, we're looking at these functions. And so what it's going to look like is you're going to have your function sort of split up into different like areas or different kind of like spots. Okay. All right. So factor w to the 4th. Okay. -81. Okay. Arlie, I'll get to the factoring question that you have after I work through these piecewise functions. But the short answer is that it's a difference of squares. How much do I have to? We just started, actually, so we've got about an hour left for questions. Okay. All right, so a piecewise function is going to be where you have a function that maybe in certain ranges, it changes, right? So with ranges, it changes. Haha. So maybe it's, you have different limits for the x values. So let's just dive into this. It's a little bit easier to explain when we have an example. So f of x, which is function notation. So it just means that the function of x is, let's say we do 2x minus 3 when x is less than or equal to 2. Okay. And then we're going to say f of x is x squared. No, we'll just start with linear functions here. Okay, so then we'll say f of x is negative x plus 1 when x is greater than 2. And then we'll say that f of x is, wait, hold on, x is less than or equal to 2. Yeah, when x is great. We'll just stick with that. We'll just start with 2 of these for now. Okay. Find all real zeros of a polynomial function. Let's see. Bingy bongy 1, 2, 3. All real zeros of polynomial functions. Is that what math are you in? Is that pre-calc or algebra 2? Okay. That helps me kind of figure out what level to go with. Okay. All right, so here is our piecewise function. So what this means is that, yeah, Bo, I can definitely do that. Let's see, parallel lines, transversal, okay. I'm just leaving my little notes down here. Okay, so a piecewise function, what this is meaning is that when x is less than or equal to 2, it's gonna follow this line, but when x is greater than 2, it follows this line, okay? So what I'm going to do is I know that x and 2, this spot here where x is 2, this is kind of like my change point, right? This is like my transition point. So anything less than over here is going to be 2x minus 3, okay? So what I can do is I'm going to figure out, all right, well, when x is 2, it follows 2x minus 3. So I'm going to do a table of values. So I have 2x minus 3. And I'm just going to make a table of values. And since I know this is a line, I know this is a line because there's no exponents on the x. So I can look at, all right, I know I want to figure out what that value is at 2. And then I want to pick a value that's less than 2 for my x because that's where else my line is going to go. Okay? So 2 and let's say 0. Right? So we've got these two values. So when x is 2, I plug in my 2 for x. So I have 2 times 2 minus 3. So that's 4 minus 3. So that's going to give me 1. And then when x is 0, I've got 2 times 0 minus 3, which gives me negative 3. So I know that when x is less than or equal to 2, it's going to pass through these 2 points. Okay? So when it's 2, my y value is 1. Now I'm going to put a point there and I'm going to fill it in. Okay? Now I'm going to fill it in as like a colored in circle because this little line here that means that it's or equal to 2 means that if x is 2, it is at that point. It is at 2, 1. Okay? So then I've got 0, negative 3, which is my y-intercept. There we go. And then I'm going to grab my little broken ruler because I forgot to grab a ruler to keep here. Whoopsa-poopsa. Okay. So I'm going to draw my line here. Just going to connect these two dots. Okay. Doot, doot. Got a little bit bloopy. Okay. Now, I know that my line is only going to be that part, right? Because if x is greater than 2, it's not going to be following this line anymore. It's going to switch. It's going to jump up to that other line, right? So now when x is greater than 2, it's going to be following along with negative x plus 1. So negative x plus 1. Again, I'm going to figure out what it is at 2, right? So negative 2 plus 1 is negative 1. Okay. And then I want to pick another value that's greater than 2, right? So we can do, I don't know, 5, right? The values don't really make a big deal out of that, right? Don't overthink it too much. You just want a value that's greater than 2 because x is greater than 2. Okay, so negative 5 plus 1 is negative 4. Nope, sorry. No, it is negative 5. Oh my God, negative 5 plus 1 is negative 4. It's been a long day, guys. It's been a long week. Any other teachers out there can attest that these weeks between Thanksgiving and Christmas are just woof. There's a lot happening. Okay, so at 2, negative 1, that's where my point's going to be. Now, I am going to leave this as an open circle, right? Because it doesn't include that 2. Because if x is 2, remember, it's going to be at 2, 1. But anything that's greater, any x value that's greater than 2, it's going to follow this one. So then we've got 5, negative 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. It's going to go here. Okay, I'm going to connect my lines. There we go. Okay. So this is my piecewise function. Okay. Let's see if we can get all of these. We can get all of those on the screen. Okay. So what I've got is when x is less than or equal to 2, it's going to follow my orange line here. It's going to follow that 2x minus 3, right? When x is greater than 2, it's going to follow this negative x plus 1, okay? So a piecewise function is really just like a function that's been split up into pieces, okay? Now here with this one, there's another piece that you might talk about, that your teacher might talk about, is if it's continuous or non-continuous. The easy way to think about that is if it's continuous, you can draw it without lifting up your pencil. Okay, so that would be a continuous piecewise function. This one, I have to draw this, and then I have to jump down and then bring it down here. Okay, there are no holes in this piecewise function. Sometimes there are holes, there are little gaps, right? But in this case, right here, even with this space, I'm still accounting for it. Like I can still get a value for x is 2, right? When x equals 2, there's still a value. It's x is 2, so y is 1. Okay. All right. So rational functions. Adrian, I've got a couple of other things on the list before. Nope, Bingy Bongy, I asked a question if it's what math level are you at for finding all the rational roots of polynomial functions? Okay, parallel transversals, and then there was one before. Adrian, with rational functions, can you give me an idea of what math level you're at, so I know what rational functions to do? Okay, so bingy bongy, you're algebra 2. Great. Okay. All right, so let me do one quick thing. So, and this does lead into some polynomial functions. So, bingy bongy, are you... So I know you're in algebra 2 and you're doing all real zeros of polynomial functions. Are you doing quadratics, or can you give me like an example of, give me an example of the question that you're being asked? Okay, Ella, I see you're factoring. I'm adding it to the list. Okay, Ella, I'm assuming you mean factoring like polynomials. Okay. Do a function where there's a slant. Do a function where there's a slant. Adrian, can you give me a little bit more information? Yes. Okay, so rational root theorem. Okay, hold on. All right, so w to the fourth rational root theorem. Okay. All right, so w to the fourth minus 81. Now this also answers a little bit. Oh, a slant asymptote. Okay. All right, so w to the fourth minus 81. So this leads into like factoring and different polynomials. So with this factoring and solving quadratics and things like that, well, this is not a quadratic, but this is a polynomial function. And this would be, well, it's a polynomial expression. So w to the fourth minus 81. So when you look at this, it's actually something that you want to recognize as, it's called the difference in squares. Okay? So if you see something that is in the form of like a squared minus b squared, right? Where that came from was the two binomials of a plus b times a minus b. Because if you FOIL this out, you get a squared minus ab plus ab minus b squared. Those two cancel out. So all you're left with is a squared minus b squared. So when you look at this here, the w to the fourth, that is a perfect square, right? The square root of w to the fourth is w squared. So if I think about this a squared minus b squared, well, my a squared would be w to the fourth, and my b squared would be 81, which is, again, a perfect square. So these would end up, we would want to write this as, oh, I forgot another parenthesis, sorry. Boop, okay. So we would write this as, you would actually have w squared plus 9 and w squared minus 9. So this is something, again, this is something that you would just kind of recognize, and it's called difference of squares. So diff of squares. Difference in squares, difference of squares. Might be difference in squares. Okay. All right. So this is getting into like factoring polynomials and also like doing all of the functions and function notation and all of that kind of stuff. Okay. Oh, hi, Pancake Mix. Where's my mouse? Ah! I have got too much stuff on this table. My goodness gracious. Okay. Oh, here it is. Okay. All right, so we did w to the fourth. Could you keep factoring, or is that the answer? So this would be, I mean, you could keep factoring. Yeah, you could keep factoring, because you could keep factoring to certainly the w squared minus 9, because that's another difference of squares. So if we had w squared plus 9 over here, and then you looked at w squared minus 9, right? We could say w plus 3 and w minus 3. That would work also. And then, sorry guys, I'm doing like 14 different things. So this would be as far as you can go. Okay, so factor completely, this w squared plus 9, that's not factorable because it doesn't like cancel out. This isn't negative. If this were negative, I could factor it again, just like I did over here, right? So when you multiply these all together, you will end up with w to the 4th minus 81. But yeah, this would be the most factored form that you could do for this one. Okay. All right. Come on, guys. Keep it cordial and friendly and kind in the comments. Okay. All right. So we have w the 4th minus 81. Okay. Oh, I'm going to put up this. Okay, so let's say M is parallel to N. Okay, so those two lines are parallel. So let's say this angle is, can you guys see that? This angle is, this one is 15x plus 12. And this one is this one is 17x minus 4. What's x? Okay, so we got some transversals here going. All right, federal spam and pancake mix. Knock it off. I'm going to go into teacher mode. Knock it off. Okay, so let's take a look at this one. Okay, so we've got some parallel lines going on, right? So these are parallel lines, and we call this line a transversal. Okay, so we've got parallel lines and a transversal. So what's really cool about these is the parallel lines make it so these sets of, like, I always call them like intersections, right? Like little intersections, they're gonna be identical, right? They're gonna be the same thing, okay? So like this angle here and this angle here are in the same location. That means they are also congruent, okay? So these are called corresponding angles, Okay. Okay. So when we look at these, ooh, I may have made this too challenging, but let's see. Okay. All right. So we've got 15x plus 12 and 17x minus 4. So with these two angles, and I actually didn't mean to mark them here, but I did. So we'll go with it. We'll just solve it. These two angles out here, those are called like consecutive exterior angles. Okay, so they're consecutive exterior angles, but they're consecutive because they're on the same side. And they are exterior because they're outside of the transversals. Okay. Okay, guys, this is ridiculous that I have to do this. Pancake mix, federal spam. If I have to tell you one more time, I'm blocking you. Okay, this is ridiculous. Okay, so here, Kylie, we can definitely do fractions because fractions are everywhere. So with these two, okay, they are actually supplementary, which means they are going to be adding up to 180. Now, like I said, I actually marked the wrong angles, but we'll just see how it goes. So we know that 15x plus 12 plus 17x minus 4, those are going to equal 180. Again, because these are consecutive exterior angles, okay? So they're going to equal 180. They're supplementary, okay? All right, so we've got 15x and 17x. We've got 32x. 12 minus 4 is 8, so that's plus 8 equals 180. Okay, we got 32x equals 172. Let's see, 172 divided by 32. Oh, it's not actually that ugly. Okay, that worked out pretty well. Okay, so if I divide both sides by 32, I actually get a fraction, which is 43 over 8. So in this case, x equals 43 over 8. Okay, so now what I can do to find out my my actual measurements, right, is I can just take that and I can plug it back in. Now that might get a little bit ugly. Times 50, yeah, that's not great. So when you plug it back in, this one ends up being like about 92.6 degrees. And so this went all backwards, guys. So this one would be, you know, about 87.4 degrees. Okay, because again, they have to add up to 180. Okay. So with transversals, again, there's lots of different relationships that happen with these angles, but ultimately there are only two angle measurements in this entire diagram. Okay? There's either, I call them the big angle and the little angle. So you could either be the big angle or the little angle, and the big angle and the little angle are always going to add up to 180. Okay? So here, might be kind of hard to see, but this is like the big angle. Okay? So that one and that one and this one and this one are all the big angle. Okay? So let's say this is 110 degrees. They are all 110 degrees. Okay? So then if that's 110 degrees, then the only other option is to be the little angle. So the little angle is here and here and here and here. 110 plus 70 is what you get. So you're either 110 degrees or 70 degrees, and that's it. Okay, those are the only options. Okay. Oh, what math do I teach? I teach all the way up through, well, I have taught basically like kindergarten, I guess. I've taught science and math for 20 years. So mainly my real jam is like algebra 2, trig. Hey, I like pre-calc. And yeah, geometry. Taught a lot of geometry. But yeah, calculus is when I start getting, ugh. And honestly, like everything before calculus and before pre-calc is just a lot more fun to me. So, and that's where I find that a lot of people, if you have struggled through Algebra 2, anything beyond that is going to be really difficult to do. Okay, so we did transversals. We did the w to the fourth minus 81. Trig function graphs. I'll try to do the trig function graphs. It's really hard to do though with the like with the setup because it's hard for me to show you like what the seeing calc done with AP Chem problems. Oh my God. Yeah, that sure is something. Okay. All right, bye pancake mix. All right. Let's see. Hi. Okay. I had to put on my teacher voice a little bit.
Oh no, what happened?
Just people being silly in the comments.
Oh.
Just bickering. Okay. You're failing your math test tomorrow. Well, maybe with that attitude, but let's change it. Let me know. Kieran, I think is your name. Or Kieran. If you think you're going to fail your math test tomorrow, bring in the comments. Let's see. Let's hear them. Okay. So find angles of a tangle? You mean triangle? Landon. Is this my student, Landon? That just had a quiz on vertices? Okay. Okay, so geometry. So Stella, if you give me a few more things about what you need help with geometry, I can get to that. Man, we have so many questions tonight. Everybody's got tests coming up. Okay.
How can people work with you if they need?
Oh, if you guys are really fully like panicking about a test or something, maybe not for tomorrow, but if you have a test or a final coming up next week, or even after break or whatever, click on the link in the Stan store and you can book one-on-one tutoring sessions with me, where we can do this setup and we've got the overhead view and all of that. So you can just book and click the link and do the stuff and book an appointment with me. And then we can work out, one-on-one and really get going on stuff. Okay. I am not going to get into logarithms beyond just like a basic understanding. Okay, so vertex of x squared plus 4x. Okay. Oh, Jalen, I'm sorry you failed in college because of fractions. Okay, Stella. Let's see. Oh, trig functions, right? Trig function graphs. Okay. Angles of a triangle, I'm assuming. Angles of a triangle. Vertex. Probability. Oh, okay. So that's all that. Okay. Oh man, 4th grade math. You are you are a saint for 4th grade. Yikes. Okay. Oh, we got a lot of triangle questions. Okay. Okay, so let me do I'm going to do the quadratics with graphing and like vertex and all of that. And then we'll get into residue formula and no, sorry, the integrals. Watching while you're in a parade. Oh my gosh. Okay. Okay, so let me do, we'll do a little bit of vertex and quadratics and things. Then we'll try to talk about trig function graphs a little bit. But like I said, it's sort of hard to graph this. And then we'll get into triangles and let's see. So parallel or perpendicular or neither by just knowing the x and y. Javier, do you mean by just knowing the x and y like the slope or the meltdown over the x and y axis? Just tell them it never goes away. Okay, so parallel or perpendicular just from the slope. Okay. Parallel, perpendicular from slope. Okay. Might be able to kind of sprinkle that one in with the rest. Okay, so let's take a look at finding the vertex of a quadratic. Okay, so a quadratic is something, if you had something, it's a quadratic function. So we're back onto functions. I told you guys everything is functions, right? So if I had something like x squared plus 4x minus 3, okay? So here we go. So x squared plus 4x minus 3. The way that it's written here is called standard form, okay? So standard form, we've got, it is ax squared plus bx plus c, okay? A lot of information is in here. So this c value is the y-intercept when it's in standard form like this, okay? So c is the y-intercept, so that's where it cuts across the y-axis. That never changes, even when we're talking about these kind of things. Another thing that never changes regardless of what kind of function you're graphing, including trig functions, another thing that never changes is that you can just make a table of values and it'll work out and it'll be fine. So that's one thing to, don't forget, you can always go back to basics, go back to your roots, right? Okay, so ax squared plus bx plus c. So to find the vertex when it's in standard form like this. So the first thing you need to find is there is a relationship between negative b over 2a. This is like the first step when you're trying to find this vertex, right? Is you've got this negative b over 2a. So when I look at this, my b value is 4. My a value is positive 1. So negative b over 2a is going to give me negative 4 over 2, which gives me negative 2. Okay? This value right here, again, gives me a lot of information, right? I've got negative 2 here. So what I can do is, this is going to be my x value for my vertex. Okay, so my vertex is going to be at this point. Now, remember, let's make a table of values, right? We can always make a table of values. Okay, so now when x is negative 2, I want to figure out what my y is, right? So I'm going to plug this in. So I've got negative 2 squared, which is positive 4, plus 4 times negative 2, which is negative 8. So we've got 4 minus 8, which is negative 4. Yep. Then we've got minus 3. So we've got 4 minus 8 minus 3. Okay, so we've got negative 7. So negative 2, negative 7. Now I also know, remember, well, actually, I do know that this is -3, but what I can also do is I can also just like figure that out, right? I can just look for my y-intercept, which is, again, it never changes, right? It's where x is 0, so I plug in 0 here. I have 0 squared, which is 0, plus 4 times 0, which is 0, and then -3, so that's -3. Okay, so I can start plotting these, okay? This point here, after I figure out that -b over 2a, this point right here, because -b over 2a is -2, this is my vertex. Okay. Because my a value is positive, I know this is going to open up. Okay. So it's going to open up. My vertex is at -2, -7. My y-intercept is at -3. Okay. How do you get standard form from a table? Okay. So we've got, let's start with this, -2, -7, 3, 6, 7. So that's my vertex. Oh, it's off the sheet. That's my vertex way down there. And then I know I've got 0, -3. 0, -3 is here. Okay. Now I know it's going to be a curve, so I kind of want to figure out another point. So I'm going to figure out what -1 is. So -1, I've got x squared, which is 1, -4, which is -3, -3, which is -6. So when x is -1, my y value is -6. Okay? I do teach algebra 2. I think I'm mad at you. Why get mad? It's such an easy thing. It's just if a is positive, it opens up like a cup. It's going to collect things, right? You can fill it up because it's positive. And if it's negative, it opens down. Okay, so -1, -6, -1, -6 there. Okay, so far I've got this nice curve happening. Now, what's also nice about your parabola is you have something called an axis of symmetry. And this axis of symmetry, this axis of symmetry is the line that you can kind of fold that parabola on, and it's a mirror image. Okay, the axis of symmetry passes right through the vertex. Okay, so then if it's a mirror image, then I've got these 3 points on this side. So I have the same points on this side. It's a mirror image. Okay, and then with the curve, just kind of do your best, right? Sort of difficult to do. And you can find more points depending on how big your graph is and things like that. Okay? Inverse function. Okay. Yeah, domain of the inverse is range of the, so it just flips. Like it's literally just, the inverse function is just flipping the x and y values, or the x and y kind of like numbers, right? So to solve it for the inverse function, you would just, instead of y equals mx plus b, you would start it as x equals my plus b, and then solve for y. Again, no matter what the equation is, that's always what inverse function is. Okay, so table values to standard form. Okay, so this is, you mean with quadratics here, Landon? Writing them in standard form and all of that? Okay. All right, so let me see. Okay. Let me pull up some values. Hold on. Let me, well, I can do this. What is the highest level of math you've taken? I took 3 years of calculus in college, and I was not a math major in college. I was a biochemistry major. but we did have to take calculus. And, you know, once I got past I had a bit of a kind of a roadblock when I was in pre-calc. I really struggled with pre-calc when I took it in high school. And so I took it again, sort of like a mini class in college. And once it clicked, I was like, oh, I really like this. This is fun. And then so I ended up taking like 3 different years of calculus. But I didn't really like it that much. And I think that's one reason why I went back to teaching like Algebra 2 Trig and Pre-Calc, is because that was when I really enjoyed it, right? I enjoyed it. It was challenging, but it was doable, right? And so that's what I always try to emphasize with my students, is that it is challenging, but it's doable, right? Okay. All right. So let's see. Okay. So when you're looking at these, so I don't really emphasize like doing the quadratic equation from a table. But what you are, oh, well. What's happening?
You're not at the very bottom of the thing.
Yeah, I know. I feel like I looked away for 2 seconds and then, yes, I can do Algebra 1 if you ask me any questions. What did you do? Nursing. Yeah, so Tickle Pickles. I did take calculus, but it's been a long time. And so my main focus is algebra 2, algebra 1, pre-algebra, up to pre-calc a little bit. But yeah, the main thing, but you're seeing like there's a lot of really good people in the chat and really good people that are giving you advice, and so that's a really good, that's a great thing. Okay, so Landon, the only thing that you're struggling with is this quadratics from a table. Okay. So let's see. I like that too. Let's see. Okay.
And someone else asked when you go live.
Oh, I go live every Thursday night is when we do MATHursday. And then on Mondays, we do Model Monday, where we talk a little bit more about STEM and like 3D modeling and design and things like that. Okay. So what? Wrong one. Okay. Okay. So with the... So figuring out a quadrant. So right now what we're going to do is we're going to write a quadratic function from a table of values. So the first thing you have to do is verify that it is actually quadratic. Okay, so let me... Actually, wait, hold on. Okay, so let's do this table of values. Okay, so we've got these values here. I'll put decimals on there. So many questions. Okay. All right, so here what we're looking at is we want to make sure that this is a quadratic pattern, right? So what we're going to do is making sure, okay. So from here to here, I'm adding 3. From here to here, I'm adding 9. From here to here, I'm adding 15. Okay? Now that, when we're looking for like a slope of a line, right, that should be consistent. So right there, you kind of go, ooh, that's not a linear equation, right? That's something else. What you do, this makes me think of a hobbit, is we look for the second difference. So this is the first difference between like -7 and -4, -4 and 5, 5 and 20. But if we look at the second difference, so from 3 to 9 is +6. From 9 to 15 is +6. And it would keep going and going and going. So that's what's called the second difference, right? Yeah, second derivative, yes. Okay. Successive differences, sure, yeah. So I prefer the Hobbit way of second differences. But so once we see that these are all the same, then we know it's a quadratic. Okay. So we're gonna pick a few points. Okay. We're gonna pick 3 points, and you're gonna make a system of equations with 3 points. Okay. And what we're going to do is we're going to make that, so we're going to pick 3 points, and I don't think we're going to be able to work this out all the way to the end, okay, because this is a pretty lengthy process. But I'm going to pick 3 of these points. I'm just going to do those first 3, and you're going to substitute them into the standard form of the equation, which again is y equals ax squared plus bx plus c. Okay, so I'm going to substitute in my x and y values. So my first one would be -7 equals a times -1 squared plus b times -1 plus c. And then my second one would be -4 equals, it's 0 plus 0 plus c. That might not be the greatest choice, but here we are. Plus c. And then my third one would be 5 equals a times 1 squared plus b times 1 plus c. And then what you would do is I don't think you should use the 0 and -4. So let's do 2 and 20 instead. It's not a very good example. Okay, so let's do 20 here, and then these are 2 and 2. So then what you would do is you would solve this system of equations to get your a, b, and c value. That's what you would do to then figure out. Then you've got your a, b, and c, and that'll get you into standard form. 0 is good because it does just give you the c value. That's true. Oh, that's true. Yeah, you could use that one. Yeah. Either way, ultimately, it doesn't really matter which 3 you pick because the equation is the equation. But yeah, that's a good point, Step Back Mike, is that 0 does just give you the c value. Yeah, so c would be -4. Then you just have to solve the 2. Okay. All right. So we did that. Let's talk about. So I've got my list here, guys. I'm gonna kind of go out of order a little bit. So I'm sorry if I don't get to yours right away. But some things are just kind of a quick little blip. So somebody had asked about parallel and perpendicular from slope, right? So when we look at the slope of two lines, the slope is how much it's rise over run, right? So how much is it going up over how much is it going sideways, okay? So between 2 points, let's see, if I have this point, I'm going to start with some positive values. Okay, so I've got here to here. Okay. So this point is 1, 3. And this point up here is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So this one is 6, 8. Okay. So my slope is rise over run, right? My slope is rise over rise over run, which means how much am I going up for every movement I make to the side, right? So I am going up 5. And I'm going to the side also 5. Okay? So my slope is actually 1. And we use a lowercase m for slope, but my slope is 1 because it's 5 over 5. Okay? So if I have a line that is parallel to that, right? So parallel lines means that they never intersect, so they're going to be at the same angle, right? So if I have a line down here that's here to there, all right? So I've got that. Okay, so they're kind of far away, maybe, right? They could be here. Thanks, Marius. All right, so this one here is -2, 1, 2, 3, 4, 5, 6, 7. So -2, -7 is this point. And here we've got 4, -2. Ah, I said 2 and I wrote 7. -2. There we go. Okay, so let's check the slope of this one. So here and here. So we've got 1, 2, 3, 4, 5. So this one goes up 5 and over 1, 2, 3, 4, 5, 6. So this slope is 5 over 6. Now that's pretty close to 1. But pretty close is not good enough. Okay? So this one here, these two lines are not parallel because they are not the same slope. Okay. Now let's look at perpendicular. So how about I'm going to kind of have to spin this around a little bit. So I go from here to here. Okay. I've got that line there. So let's see. So this point here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this point here is -9 and 4. Here, let's see. 1, 2, 3, 4, -4, -2. -4, -2. Okay. I do not teach calculus. Let's see. Angel. What do you need help on? Let me know your biggest thing. Oh, systems of equations. Yeah. Thoughts on complex analysis? It's complex. No, I have no thoughts on complex analysis. Okay. All right, so I'm going to look at this slope, which I kind of messed up, and I sort of marked it a little too close. Okay, but here I've got it going over 5, and it's going down 6. Okay, so my slope for this line up here is down 6 and over 5. So that's -6 over 5. Okay, so when I look at this slope of -6 over 5 and this slope of +5 over 6, these are two perpendicular lines. So so parallel lines means that they have the same slope. Perpendicular lines means that they have the opposite and reciprocal. So opposite is positive or negative. You flip the sign. And reciprocal means that like this, right? 6 over 5, 5 over 6. 1 over 3, 3 over 1, right? So they have to be both opposite and reciprocal, okay? So negative 6 over 5 and 5 over 6, those are perpendicular lines, okay? All right, we got just a few minutes left. Let's see. We did that. Okay, so decimals, a little bit of decimal work. Okay. Hardest math class for me in college. Probably the third. Well, it wasn't a math class. It was because my math classes, like I said, once I got over my roadblock that was preventing me in pre-calc, I was able to get through a few different ways. I was able to get through a few different calculus classes. The hardest class for me though, which had a lot of math in it, was PChem, physical chemistry. It was basically I was a biochemistry major. I was all about the chemistry stuff. But what it was is it was basically like the physics of why the atoms were in the arrangements that they were in. I genuinely think my professor just took pity on me and just passed me and just said, you're fine. Just go. It was absolutely awful. Statistics. Statistics is okay, but I had to take statistics classes for I had to take a statistics class, but it was for like science majors, and so when I was taking, like, it was very useful actually, and now I do some statistics stuff. Let's see. X1 times X2 plus Y1 times Y2, and if it equals 0, it's perpendicular. Ooh. That's the dot product. Oh, man. I like that. I should teach that to my upper school kids. Oh, man. Calc 2 final. An entire stats teaching live. Make some appointments through the Stan store, and I'll teach you statistics. Tickled Pickles, you should definitely be a math teacher one day. It is the best. I love teaching math. It's really fun. There's a lot of different fun ways to try teaching math, and especially if you're good at explaining it. I love math. And I love teaching math. I was just showing my students some fun little algebra things that you could do today. I have time for maybe like one more question. I could probably work out one more question. Maybe two. Let's see. Oh my God, the chi-squared. Woo! Chi-squared analysis, yes. There's a lot of stuff. Solving equations with rational exponents that also has an extraneous solution. Oh my God, CJ, you are hitting me right. That is a heavy question to ask right at the end. Okay, so while I am pulling up some problems to help you through that, let me put up a couple of fraction problems on the board that we can do. Let's do that one. Let's do 2/3 times 5/6. All right, so looking at these, and then we'll talk about some rational exponent equations and things like that. Yeah, rational exponents. Yeah, rational equations. Okay, so 1/2 plus 3/5. So remember, you've got to make sure that we have a common denominator, right? So we've got 1/2 and 3/5. So we want to make sure that we have the same size of pieces that we're talking about, right? So the easiest way to find a common denominator is to multiply the denominators together. So we have 2 times 5, which is 10, right? So we're going to make both of these over 10, okay? So 1/2 is 5/10. 3/5 is 6/10. So what I end up with is I just add 5 plus 6 and I run out of room, but I get 11/10. Okay. And then here we've got 2/3 times 5/6. Multiplying fractions is the easiest one because you just multiply straight across, right? So I get 10 over 18, but then I can simplify that. 10 and 18 are both even numbers, so they're divisible by 2. So I've got 5 over 9. Boop. There we go. Okay. Back to Algebra 2. All right. I keep forgetting that these are little erasers, and I keep looking for like my little baby socks or my little rags and things. Okay, so you can convert to a mixed number, or a lot of times in sort of like upper level maths, you leave it as an improper fraction because if you're graphing it or something like that, you don't necessarily need to simplify it. You can convert it into a mixed number if you need to, but when you're graphing it, not every teacher requires it. So let's see. Multiplying is just straight across. The cross multiplying, I think you're thinking of division, which is where you multiply by the reciprocal. Because something like times 1/2 is the same thing as dividing by 2. Okay. So guys, I'm kind of on my last little bit. So we're going to do some solving. Okay, so let's see. All right, so let's look at some radical equations. So we've got, let's look at 3 plus square root of 2x minus 3 equals 8. Okay, so if we have something like that, right? Our variable is in here, it's underneath the radical, so I need to get it by itself, right? So just like I start off with basic linear equations, I'm going to subtract 3 from both sides, and I have root 2x minus 3 equals 5. Okay. So then to get rid of this radical, now that it's by itself, I can square both sides. So the square root squared, those cancel each other out. So all I'm left with is 2x minus 3 equals 25. Add 3, add 3. I've got 2x equals 28, right? So I've got x equals 14. Now I want to check and make sure that I can plug it back in up here and that it still works, right? So an extraneous solution would be where it doesn't actually work back in the original equation. So 14, so if we do, usually you just kind of type this into your calculator, but so if we check it and we go, all right, so let's see what 3 plus the square root of 2 times 14 minus 3 is, right? So 2 times 14 is 28. 28 minus 3 is 25, right? So now we're looking at the 3 plus the square root of 25. Square root of 25 is 5. 3 plus 25, or 3 plus 5 is 8. So this is a solution, right? Because up here we had the equation that equals 8. Okay? So the fact that we plug this solution back in and it does work, it's not extraneous. Okay? Let me see if I can find one with an extraneous solution. Oh, that one's not there. Okay. I don't remember who was asking for this. Let's see. Oh, I don't remember who was asking about this. Oh, CJ. Oh, that's right. CJ, you were asking for... Oh, yeah. That was you. Haha. Well, so I couldn't... Is this what you were looking for? So this is with the radical. But you wanted some with the rational exponents? Okay. Let me see if I can find one that has a... They're just hard to, like, make up. Okay, let's see. Most of them are all radical. Okay, so we want to always make sure that we've got, like, that you check for the... that you check for the extraneous solutions, right? That one doesn't have any. This one might. Okay. Okay. So let's just work through a rational exponent equation. Just in and of itself, and we'll just double check those, right? Okay, so if we have, and this is going to be my last problem of the night, guys. So fad tracks, I do take, so guys, I do these every week, every Thursday. But remember, you can also send me a message, and so I can work this out right at the beginning. And you know, I would love to stay on here with you guys for a couple of hours, but I really can't because I have to get up and teach in the morning. But you can also check out my Stand Store link, and you can make appointments to be like one-on-one tutoring with me. So go ahead and, you know, make sure you check that out. But let's see. Okay. So let's do this rational exponent, right? So let's do 3 times x plus 1 to the 2/3 equals 12. Now, just like we did with the radical equations, we want to get that x by itself, but also we just want to make sure that we've got that by itself, because this is technically like a radical symbol. So we're going to divide both sides by 3. Okay, so we have, we still have x plus 1 to the 2/3 equals 4, right? So now this is where you get into that like whole multiplying by the reciprocal. It does cancel it out. So this is kind of going into like multiplying by the reciprocal. It's doing like exponent rules, all that kind of stuff. So what I'm going to do is I am going to put this, I'm going to multiply or put this to the 3/2 power. Now what that's going to do is this 2/3 times 3 over 2, those are going to cancel out. So all that's left over here is x plus 1. Now over here is where it gets pretty interesting. So we still have to multiply this or put this to the, oops, not the 2/3, put this to the 3/2 power. Okay. Now when you have a rational exponent like this, the denominator becomes the radical, like the root, and then the numerator becomes the power. So this 2 drops down to make this a square root, okay? And remember, plus or minus, right? Plus or minus the square root of 4 to the 3rd. Rational exponents are kind of bonkers, right? So the denominator, so here we have the denominator, which was 2, and that became the root, so it's a square root. And then this numerator became the exponent, which is pretty cool, right? So we've got 4 to the 3rd, and what's 4 to the 3rd? Well, 4 squared is 16. 16 times 4 again is 64. So now I'm looking at x plus 1 equals plus or minus the square root of 64. What is the square root of 64? Plus or minus 8. So we've got x plus 1 equals plus or minus 8. So this is where we kind of split our values, right? Either x plus 1 does actually equal 8, which means that x equals 7, or x plus 1 equals negative 8, and x equals negative 9. Right? So we're going to check these by plugging these back in, right? So if we plug it back in, we would get, and it's easiest to just do this on your calculator, right? So you would just plug back in, you would go 3 times 7 plus 1 to the 2/3 power, and you get 12. And then you would do that again, 3 times negative 9 plus 1 to the 2/3 power also equals 12. So these are both correct solutions. These are both valid solutions. Now, if I were to plug this in and I get a number other than 12, then I know it's extraneous, right? So I would it would be an extraneous solution. Can I turn 4 into 2 squared, then raise it to 3? Yeah. Yeah, you could definitely do that. Yeah, CJ, that's a great idea. Because then 2 to the 3rd, but then you do have to remember that it's plus or minus 2 to the 3rd. Right? Because even though it's canceling out, you do have to remember that it's that plus or minus 8. Right? Because really, you don't even have to worry about the plus or minus until you actually take the square root, right? Unless this was not a 60, right? Unless this was not a root of 64, a perfect square. So you could absolutely do the 2 to the 3rd thing. That's a great idea. Why is it plus or minus? So the reason it's plus or minus, anytime you have a square root, it can be plus or minus because 3 squared is 9, but also negative 3 squared is also 9. So if you take the square root of 9, sometimes you don't always know if it's the positive or the negative, okay? All right, guys, have a wonderful night. Good luck on all of your tests. I know a lot of you have tests tomorrow, and I'm sorry I couldn't help every single one of you. I want to help every single one of you. But know that you're all going to do great. You're going to do great things, and keep up the hard work and keep mathing. All right, good night.